We'll be talking about, oh, sorry, Christine. Today we'll be talking about data analysis with Python. My name is Kaylee Nelson. I work on the research support team at the Yale Center for Research Computing. And if you want to get in contact with us about any questions about this presentation or any of the research computing services that we support here at the center, you can reach us at research.computing@yale.edu. If you have any questions, and feel free to ask them if you do, just post them in chat and I'll do my best to answer them. And we can always unmute if it's a sort of more involved question. So let me get situated. So data analysis with Python. Python, when it was originally written, was more of a general purpose programming language than R or MATLAB, which you sort of may have traditionally seen for statistical analysis and other types of data analysis. But Python has gradually become more popular for data analysis and scientific computing over the last decade or so. But you do need to install some additional modules in order to get this functionality. So some of the more popular modules that are used for data analysis are, you may have heard of some of these or all of these. NumPy, which is an n-dimensional array package. SciPy, which is a scientific computing package. So things like linear algebra, numerical integration, optimization. Matplotlib, which is a 2D plotting package. It is my understanding that actually it's pretty well inspired by the way MATLAB does plotting. So if you're familiar with MATLAB plotting, Matplotlib may feel like a second home. IPython, which is an interactive console. SymPy, which is for symbolic mathematics. And then lastly, Pandas, which is a really powerful data analysis. So basically, the way Pandas came along was, I think the Python people, the Python community, became jealous of the data frame structure that's available in R and wanted to do something in Python. And so it's very similar to that. So today, in this presentation, we'll be talking about a few of these. We'll be talking about NumPy, Pandas, and Matplotlib. So first of all, if you don't already have these packages, how do you get them? The best way to do this for your laptop or a lab machine is to download Anaconda. If you just Google Anaconda Python, it will come up, but the link is also in this presentation. It's a super easy installer. It works on all of the operating systems, and it includes all of the packages that we'll be talking about today right out of the box. But it's also really easy to add additional ones just using the conda command or the Anaconda interface. We also have a version of Anaconda that's available on the clusters called Miniconda, and we have instructions on our website on how to use that, but it will also allow you to add whatever packages you need and get these on the clusters. So before we jump into the additional packages, NumPy and Pandas, we'll do a brief refresher on Python data structures, just to make sure that sort of we all are up to speed on what is available in base Python, since a lot of the paradigms and patterns that are used for the native Python data structures are reused in the more advanced packages. So the first one is lists, which are the most commonly used data structure. They're just a collection of values where values can be any data type or object, and they don't even have to all be the same. So here's how I instantiate a list of integers. A list is defined by a square bracket and then comma separated values. So here you can see I set it to be this 4-element list. You can do floats, so numbers that have decimal points. You can also do strings. And then of course you can mix things. They don't have to all be the same data type. And this can be a little bit different from what you may have seen in other programming languages, but it can both be really powerful and a little bit of a trap. So just be aware. So how do you access a list once you've created it? The way you access lists and all list-like objects in Python is to do the variable name of your list and then square bracket notation and then the index of the element that you want. And Python is in fact a zero-indexed language, which means that the first element is indexed by the number 0, and the second element is indexed by 1, and so on and so forth. So this should return us the third element in our int list, and it does. but you can get a little bit more fancy. You can also select what are called slices, which are ranges of values. And so this will return 2 values, starting with the second value, and then including also the third value. So if you remember what the int list looked like back here, it was 199,334. And so the slice returns 33. You can also index with negative indexes, which will give you the index starting at the end. So -1 will give me the last element in our list.
Kaylee, can you make that a little bit bigger?
Sure. Is that better?
Yeah, that looks better on my end.
Okay. We may wind up with some things rolling off the bottom, but we'll get there. We'll fix it when we get there. So to add to a list, you can use the append function. So you take your list variable and then use do dot append and then the value you want to add to it. And that will put it at the end there. You can also join two lists. In programming speak, this is called concatenating. And you do that by simply just adding them together with the plus operator. So if you remember our string list, which had like apples and oranges and grapes or something in it, and then I create a new list called with pineapple and mango in it, if I do my string list plus additions to list, it will return a new list that has all 5 of those elements in it. And this is called concatenating. So dictionaries are another really powerful data structure in base Python that are comprised of key value pairs. So for every pair, there must be a key, which has to be a string, but the values can actually be any data type. And they don't need to be all the same, and they can be actually fairly complicated data types. They don't have to just be ints or strings or floats. They can actually be lists or even additional dictionaries. So I'll create a little dictionary here for this workshop. So my keys are here on the left, and then the value, and then it's colon, and then the value, and then comma, and then the next pair. And you can continue this on until your dictionary is defined. And dictionaries are defined by using curly braces instead of square braces like lists. And so the way you index a dictionary is similar to a list, but instead of passing it an index in your square brackets, you pass it the key, and it will return the value that went along with it, which for this case is a datetime object for today. You can also, so here under topics, I included a list of topics, and when I index for topics, I get that list back. I'm gonna make it small just for a second. You can ask the dictionary for all of the keys if you want to just check that the key is present or get a list of the keys for whatever reason. You do that with .keys. Similarly, you can get all the values with the .values method. So the way you add a new value to an existing dictionary is you index it with the key as if the key existed, and then pass it what you want the value to be. So we didn't previously have a location key, but here I did bootcamp location equals, well, it's not 160 St. Ronan right now, it's my house, but you get the idea. It returns an address. Other common data structures are that just you should be aware of in case you ever come across them are tuples, which are just like lists except that they are immutable, which is sort of programming speak for they can't be changed. And you'll know you're working with a tuple instead of a list because instead of initializing it with square brackets, you use parentheses. So this will return, otherwise it behaves exactly like a list from a reading perspective, but if I tried to change one of these values, it would tell me that it was a tuple and therefore cannot be changed. I haven't often come across an instance where I need to create a tuple, but they will sometimes get returned by functions. And so it's useful to know that if you print it out and you see the round parentheses, that what you're dealing with is a tuple, and you might get an error if you try to modify one of the values in it. The other common data structure in base Python is sets. Sets are, again, like lists, except that they can only contain unique values. So for example, if I create two lists, one that has 1, 5, 7, 3, 9 in it, and then a second one that has 3, 6, 5, 8, 2 in it, there's a couple values that appear in both of these lists. If I concatenate them together using the plus sign operator, and then I cast them into a set, if I print it out, it will return an ordered version of the list that only contains the unique values. So there aren't 2 3s, there aren't 2 5s. This can be really powerful in certain circumstances when you do only want to get a list of the uniques in a very large list of numbers. Sets are very efficient at doing that operation for you. So they're a little niche, but they can be really powerful if you need them.
Kaylee, we have a comment here in the chat.
Sure.
Side note, I thought keys of dictionary can be integers too.
I don't think so. I think they have to be strings, but I mean, I guess we can check. Go back to here. Go back to my dictionary. And try and add another new value. So what if we make this a 2? Oh, yep, you're right. They can be integers as well. They can be integers or strings. Good catch. I will update that in the future. So those are the data structures. For loops in Python are an interesting beast. I'm sure everybody's used them, and they're an absolute necessity in all programming languages where you're doing basically any kind of scripting. The way you use them in Python is a fairly intuitive syntax of for, the index you want to be indexing over, in, and then the list of things you want to loop over. So here I'm using range, which will create a list of 4 numbers. And then I'm just going to ask it to print out each of the values in range 4 and add 3 to them. And so this prints out 3, 4, 5, 6. But the problem with loops in Python is they're actually really computationally inefficient. So when possible, which definitely is not all the time and isn't always necessary if you have a fairly short loop, you can try to be a little more Pythonic in the way that you create or traverse lists using a thing called list comprehensions. So this is useful for a couple reasons. One, it's much faster. The reason that Python for loops can be kind of computationally inefficient is that since Python is what's called an interpreted language, meaning that when it runs Python scripts, the computer runs them one line at a time, which means they don't really know what's going to happen next until they get there, which means it kind of has to leave a lot of opportunities open, and it can't optimize to the degree that a compiled code like C could, where it knows exactly what's going to happen when it actually runs the executable. So therefore, for loops are this like super open-ended operation where anytime it goes to the for loop, anything could happen, and therefore it can't optimize. So list comprehensions help solve that problem because they tell Python that for every element in this list that we're going to go through, we're going to do exactly the same thing. And therefore, it can optimize that operation quite a bit. I also find that they're a lot easier to read compared to a for loop. And we'll take a look at that now. So here's a list I'm just going to create. So this is the way you would do an operation in a standard for loop, where we want to multiply each value in my list by 3. So we create a new list where we're going to put the new numbers. We're going to loop through each item and the number using enumerate here, which is sort of a fancy for loop thing, which gives you both the index of the value and the value itself. I don't actually wind up using that functionality here, but I thought it would be useful to show. And so then to my new list, I'm going to append the number from my original list times 3, and then I'm going to print out my new list, which is quite a few characters to basically do an element-wise 3 multiplication. In a list comprehension, you can do this in one line. So list comprehension takes the form of, again, you use square brackets because we're working with lists here, and you say the operation you want to do for the value across your entire list. And this will just return the same output as this much longer, more complicated, harder to read version. And it's more computationally efficient. So for a 5-element list like we're doing here, I think the speed up is negligible. But if you were looping over thousands of values, you would definitely notice a difference between these two. So dictionaries also have comprehensions. So if we have 2 lists here, Seattle, San Francisco, Dallas are my cities, and then in there I've created another list that's got the number of people who live in each of those cities. You can create a dictionary from these 2 lists using a dictionary comprehension. And because we're dealing with dictionaries, we have curly braces instead of square braces. And so sort of working from the back to the front, the first thing I do is zip cities and the number of people together, which creates a zipped list. So basically it's a list of pairs of this value and this value, and then a pair of this value and this value, a pair of this value and this value. So then I'm going to say that in each of those pairs, I've got a city and a people, and I want to map that into a dictionary where the city is the key and the number of people is the value. So if we print that out, you can see that it took my 2 lists and put them together into a dictionary. This is really nice thing to do because now I don't have to remember that the second element in both of these lists is the San Francisco value. You know, you could see a way in which this could very easily get messed up if I prepend or append or change something about number of people. All of a sudden, all of its connection to what these values actually mean, what cities that they correspond to, gets lost and kind of jumbled. By putting them in dictionary, it's all right there in an obvious way, and it can make for much safer computation. So we can, since it's dictionary, we can now just ask what the population of Dallas is. So that's it for what we'll be talking about for basic Python operations. And now we're gonna talk a bit about NumPy. Before we do that, are there any questions on Python, the basic Python data structures and for loops?
So Python's not vectorized like something like R is. Like you gave that example of creating a new list where you're multiplying each one by 3, where in R you could just do like the vector times 3. So that's
yeah. Right. So you'll see when we move into NumPy that it starts to give some of that functionality. I like to start off with the Python basics so you can kind of see how clunky it is, and then you can appreciate to some extent what NumPy and Pandas gives you. And there's some things in NumPy that we'll see that are kind of clunky, and then you'll see how smooth they are when you do them in Pandas instead. But yeah, since Python was written as just a general purpose scripting and programming language and not for math and data analysis, out of the box, it is kind of clunky to do some of these mathematical operations. But NumPy and Pandas exist and so that they can smooth a lot of those sort of speed bumps up for you. Yeah, thank you. Any other questions? Great. So NumPy is really, excuse me, the foundational package for data analysis in Python. It underlies most other data analysis packages. It's extremely efficient for all types of mathematical operations. Particularly, you'll see this in large data sets. It's because under the hood, NumPy actually uses C code. So it's much faster than running the raw Python equivalent. You can, not only is it good for doing mathematical operations, it can also be used to help you store and manipulate tabular data. I'll show that, but we'll see that Pandas is even better at doing that. So the first thing you need to do, because NumPy isn't baked into base Python, is you'll need to import it. And there's a convention in the Python community to always import NumPy as NP, and so we'll follow that here. You'll often see this if you read other tutorials or Stack Overflow. And so I think it's helpful to be aware that this always, if you see somebody just say like np dot some method, they're talking about a NumPy method. So we'll import that. And so how do you create what the list-like thing in NumPy, which are called n-dimensional arrays? And there's lots of ways to do this. So this first way I'm showing is we're going to initialize an array that is just full of zeros. What I'm passing here is the shape of the array. So I want a 2x3 array. And this is how it prints it out. So we have 3 columns and 2 rows. in this array, and they're all just initialized to zeros. But if you have a pre-existing list, you can also pass that list to lists to create an array. So here I've got a list. This will also create a 2 by 3 array, but it will have values in it based on lists that I pass. You can also use the NumPy equivalent of range. So range creates a list of a certain number of elements. NumPy has a version of that called numpy.arange, and it does the same thing. You'll always know that you're working with a NumPy array as opposed to a list, because it will say array here when you print it out, wrapping around a list-like looking object. So how do you get values from an n-dimensional array? And there's lots of different ways to do this, and we'll sort of walk through the basic ones that might be useful. So first of all, if you just want a single element out of your 2D array, you can index it. Again, it's the same as lists, except that now you can index across multiple dimensions. So instead, normally in a list, you would just do A0 to get the first element. But because we're working with a 2D array, we need to also pass it a column. So we have 0, 0. One of the really nice things about the way the data packages work in Python is they will always return you the most primitive object, the simplest version of whatever it is that you want to be getting back. In other programming languages, if you did this, you may get a list or an array that contained a single element. Instead, Python reduces it down to just the scalar, so you get just the integer. This is really nice. So we got the first value of the first column and first row. You can also, again, using this colon notation that we used for slicing, you can get an entire row. So if you do A0 for the first row, comma, and then the colon, it just says, I want everything in that row. I want all of the columns. And so it will return you a one row array. Similarly, you can ask for an entire column. Here I'm going to ask for the last one. So the same colon notation, comma, and then -1. And so this returns the last column. Notice it returns it as a row, not as a column. I'm not entirely sure why it chooses to do that, but that's fine. If you wanted it to be in a row or in a column, you could do a reshape. I think you would do it like something like this. I don't remember exactly the syntax, but you can use the reshape command to turn it back into a column if for whatever purposes you need a column. But the important part is you get a 1D array instead of a 2D array. You can also get a submatrix, so the same slicing can be used across both the columns and rows to get a smaller piece of your overall data. So those are the basics. It builds on the same idea of how you index a list, except it adds in the idea of grabbing entire rows and columns, and the idea that you are now dealing with a 2D data structure as opposed to a 1. So if you want to modify elements in your array, so we'll start with our array here. You start with the same idea of how you index, and then you pass it a value. So here's how I replace the first element, the first row and column, with 25. And you can see that that got updated there. But you can also pass it in entire rows. As long as whatever you're passing, shape, so the number of elements in it, matches the selection that you've made with your index here, the operation will work. So here I'm replacing the entire first row with 10, 11, 12. Similarly, you can also pass it a column. And it's smart here, I don't need to reshape this into a column, into 2 rows. It says, okay, you've given me a 2-element 1D array, and you're asking me to overwrite a 2-element portion of your array. I can figure out how to interpolate that for you. You can also overwrite a submatrix, so the same submatrix selection we made before. As long as I pass it a 2 by 2 array, it will put that in place. So that's all pretty straightforward. You replace with kind, but arrays also let you do this additional type of modification called broadcasting, which is where in your index you actually select multiple values, but you only pass it a single value. And it knows that what you want to do is put 10 in every element of the first row. So instead of just replacing, instead of, you know, barfing and saying, oh, you passed me a single element, but you asked for a 3-element index, it actually knows what I want it to do is to put 10 in each of these things. Similarly, you can overwrite all the rows. Here's how you select the entirety of all of the contents of your array. You can actually use the colon for both the row and the column. So here I'm passing it a row and I'm saying overwrite my entire array with this row. And so what it does is it repeats the row for as many rows as my array contains. Similarly, oh, there's the reshape syntax. Similarly, I can do this with replacing a column. Here I do have to make it look like a column before I pass it on. Otherwise it's ambiguous whether or not I'm trying to tell it to overwrite the rows or the columns. So here I pass it my column, my 2-element column, and I say overwrite my whole array with that. So we get 40, 41 for each column. Similarly, you can broadcast to a submatrix or any combination thereof. This can be really powerful if you want to like say you want to zero out a section of your data, or you want to initialize an array with all one value, or one version of that or another. The broadcasting can make it much simpler than looping through the entire array to replace the values. So now that we know how to create arrays and modify them, now let's get into the actual functionality that they provide for us. So operating on arrays, you just use binary operators, so plus sign, minus, multiplication, division, and you can also use some additional NumPy functions. So we'll create a little, just a short 4-element array here. You can add 1D arrays element-wise, which means that the first element will be added of one array will be added to the first element of the second to the second, the third to the third, the fourth to the fourth. So here you can see that we just added this array to itself. So the new values are 0, 2, 4, 6. You can also do multiplication. So if we multiply them, each element is now replaced with the square. So 0, 1, 4, 9. You can also do multiplication by a scalar. So if we want to just multiply every element in our array by the value 3, you just do that by doing 3 times the array. Now, if you remember, we compare this to the lists. The list comprehension was nice and very readable and returned the same result, but the NumPy is faster, and I would argue even easier to read than the list comprehension was. And so this is where you really get into the value of using NumPy versus this type of operation in base Python. I think there's a lot to be said for readability in code. It makes it easier not only for you to share your code with other people, but also for your code to be more robust, even if it's just you editing it, because it's always more clear of what operation you were intending to perform. There's also, in addition to the basic operators, the plus sign, minus sign, multiplication, NumPy provides a number of additional methods that can do more complicated mathematics on an array. So here we take our 1D array and we're going to ask NumPy to sum up all of the values in it. So this just adds every value in the NumPy array and returns the result. You can also get fancier. There are functions for performing dot products. So this is the dot product of those two two arrays. So there's a lot of matrix operations that are built into NumPy. So here's doing a cross product. So we do a dot product of the reshaped versions of the array. There you can look in if you're in IPython or a Jupyter Notebook, you can see by using tab completion all of the operations that are available to you as part of the methods on an array. So for example, you could also ask for the mean, and this will give you the mean value of all the values in the array. You could ask for the max, that'll give you the maximum value of all the elements in the array. So there's lots of very useful functions that are built right into NumPy arrays and NumPy itself as additional functions for doing any type of matrix operation or sum or mean, those types of statistical analysis. So those are the basic mathematical operations that you might want to perform with NumPy. It also can be used for working with tabular style data. And so for this, I'm sort of referring to data that you may get in like a CSV. I'm going to show this because I think it's useful to know how it works. But you'll see when we get to pandas that there is a much sort of better way. So since my background is in astrophysics, all our examples today will be sort of solar system themed. So here I'm reading in a CSV of some solar system data and using NumPy to read it in. The best way to read in a CSV directly into NumPy is to use the gen from txt function, and then you pass it a number of things. So you pass it the file, you tell it what the delimiter is. So here it's a CSV, so I tell it it's a comma. But you can also say if you've got like space delimited data or pipes or whatever, you can pass that here and tell it what to do. I'm telling it that the first line of my CSV is a header. It just contains the column names, and so it shouldn't try and read that in as data. And then when one of the more clunkier parts of doing this with NumPy is you have to tell it what to expect for the data type of each of your columns. And so here I'm telling it that there's a string of maximum 10 elements, a string of maximum 20 elements, an integer, and then 2 floats are my 5 different columns. But then once you do that, it does a pretty nice job of reading it into a table, into a 2-dimensional array for you. So you can see what we actually contain in our CSV is a bunch of celestial bodies, what type of body they are. I think this is the order from the sun, and then either the diameter and the mass or the other way around. So as you can see, without looking in the CSV, it's not obvious what perhaps these 3 last columns are. And so we want to label them. And you can do that in NumPy, which turns this into what is sometimes referred to as a record array. So the way you do that is you take the NumPy array that contains your data, you do .dtype.names, and then you pass it a list like of the same size with the column names for each of your columns. So it was planet, type, order, diameter, and mass. And then when you print it out, that information is now stored in with your data, which can be very useful for making sure that when you are indexing the correct thing and you aren't getting your columns confused. And it actually means that you can straight up index by these column names. So solar system data and then indexing mass will return me the mass column. And then I can do since that at that point is just a NumPy array, I can use any of the mathematical operations we just spoke about on that column. So here I can get the mean mass of the celestial bodies contained in my data. You can also do mathematical operations on that are slightly more complicated using any of these columns. So here I'm calculating the volume of Earth. So the formula for volume and what I'm passing into it is the diameter of the 4th element of my list, of my NumPy array, which I have to remember corresponds to Earth, which is a little clunky, and you'll see ways to improve it when we get to pandas, but it does in fact work and return the volume of Earth in whatever units I happened to put into the CSV. You can also do linear algebra. So this is sort of getting back into sort of the matrix operations. NumPy has a really powerful linear algebra sub-package called linalg. And so here I'm just going to create a basic array. If you are interested in linear algebra operations, I recommend you just look up this package and see what's available to you. But I'll show a few things here. So if you want to compute the inverse matrix of the matrix you pass, you do linalg.inv, and that will return the inverse matrix. You can also do singular value decomposition. You can compute eigenvalues. So there's lots of really powerful matrix operations that are also provided to you using NumPy. So before we move on to pandas, there's one sort of caveat that I want to talk about with NumPy, which are called views. So views are basically arrays that share the same memory with another array. And what do I mean by memory? So whenever you write basically any kind of data or read any kind of data into your machine, like you create an array, for example, in a Python script, what it does is it actually stores each of those values in that array somewhere in the RAM on your computer. And if you had two arrays, in theory, it would create it would use two sections of your RAM to store each of those arrays. The way views work is there are actually multiple arrays in your Python script that actually point to the same buckets of memory in your RAM. And this can be really powerful because it can make your program more memory or CPU efficient, because if those arrays may have different names but contain a lot of the same data, like data that is linked in some way, you don't necessarily need to duplicate double the amount of storage it's going to take. And so views are the way that NumPy tries to be smart about this. You can explicitly generate views using a special method called view, but sometimes views will just happen. Like there's something that certain NumPy operations will use views versus not use views. And sometimes it can be confusing when this happens. So reshape and transpose both return views of your original array. What that means is if you had an array of one shape stored in a variable, so therefore in your memory, and then you ask NumPy to reshape it, it won't create another section of storage buckets in your RAM with the rearranged values, because all the values are already stored in RAM. It just needs to point to them in a different order. Slicing is similar. It also just points to a view of the original. But this can sometimes be confusing, because if you slice data and you put that into a different variable and then you start working on that other variable, what could happen is the original array that slice was taken from will also change. So this is why I always mention this, because I've seen many times where people will take a slice or a reshaped and they assume that they're working on a standalone copy, but then they go back and do something with the original array that they reshaped or sliced, and are surprised to find that some of the values in it have also changed. And that can create bugs and confusion. So there's a couple ways to A, check if what you're working on is a view, and B, explicitly avoid a view if you're worried about it. So here we're just going to create a little range. What we're going to do is we're going to create a slice here. This is kind of a fancy slice where I'm telling it, starting with the second element, or sorry, the third element, the 2 index, I want every other value. So it's going to be 2, 4, 6, and 8. So this is a slice of the original array. So first thing I can do is I put that second slice into a different variable b. So the first one was an a, and then we've got our b. The first thing that we can do is we can see whether or not b owns its own data. So a, since we created completely afresh, does in fact own its own data, but b is a view of a. So therefore, b.flags.ownData is returned false. And we can see the implications of that here. So if we change the first element of b, which was the 2, to 100, and then we print out a, we'll see that a also changed. So this is just something to be aware of in case you ever do an operation like that where you are working on a slice. Just be aware that there's a potential that you could be modifying the thing you sliced. The way you can avoid doing this is to use .copy. So if instead, when we created the slice, I did .copy, b would have been its own thing. This would have returned true, and a would have been unchanged in this operation. So here, this is just a fancy way of checking to see whether or not they are in fact the same thing in memory, and they are not. So that's what copy does for you. It's just something to be useful, that can be really useful if you're working with subsets of your data or a reshape of your data, that you just be aware of, because it does trip people up. So I think with that, we'll move on to pandas. But before we do, are there any questions about NumPy? Great. We're moving right along. So pandas was basically created out of envy for R's data frame structure, I think more or less. People realized that they're working with more and more tabular data inside Python, and having a package that was designed to deal with this tabular data in a number of ways was more efficient than working with the very powerful but sometimes very clunky record arrays would be a nice addition. So basically it adds a new data structure to Python that's called a data frame. And again, if you've ever worked in R, the data frame structure in pandas will feel really familiar to the data frame structure in R. Another way to think of the data frame structure is it's almost like an in-memory database, as in you can it stores a bunch of tabular data, but you can query it and do all sorts of operations like that, like you would on a database. So just as NumPy has a convention of being imported as NP, pandas has a convention of being imported as PD. And so we will follow that convention in this presentation. So I lied, there's actually 2 data structures that pandas adds. In addition to data frames, there's also a data structure called a series. So a data frame is a 2-dimensional data structure. It's comprised of rows and columns of tabular style data. A series, on the other hand, is the data structure that makes up a single column, or actually row, of a data frame. So basically a data frame is made up of a bunch of series, is kind of the way you can think about it. So certain operations will return a series as its own, as a standalone data structure, as opposed to returning a smaller data frame. But the thing to be aware of, and this is one of the things that pandas adds, is for both of the data structures that it provides, there is also an index, which will show up, and it uniquely identifies each row in your series or data frame. So if you create a new series or data frame, pandas will automatically assign an integer ID as your index. But if you have a column in your data that you want to use as the index instead, you can tell it to use that column instead. Since it is an index, by definition, the requirement of using the column as your index is that every value in that column has to be unique. You can't have any repeats in an index, or else it would be difficult to actually index your data. So a series is like a data frame, but it can only have 1 column. But it will look like it has 2 columns when you print it out. So here's a little series that I made. So I just asked NumPy to create me a NumPy array of 5 random values. And then I'm just passing that to pandas. So this is one of the ways where you can create a series. pd.series, and then you pass it a NumPy array. And what it did is it turned it into a series. And this is what a series looks out when you print it out. So here are the 5 random values. But this first column, that's not really a column, that you see here is that auto-assigned index. So these are the index values of my series. And then at the bottom, it includes what data type a column is. So any individual column in a data frame or in a series does have to be of a single data type. You can't mix like a list in Python. So here I can overwrite the index. And so instead of it creating it with an auto-generated series of integers, I can tell it what I want the index to be. So here I'm going to pass a bunch of subjects. We'll like pretend that these are scores or something like that. So instead of having 0, 1, 2, 3, 4 here in this first index column like thing here, we instead get the index I passed. So a data frame is just it's sort of like a 2D version of it's a collection of series is really the way to think about it. So if I take the same data, I tell it here, since we're working with a data frame now, I can actually label the column and I pass it the same index. And so I apologize that this shows up really small. This is sort of a function of the slide package I'm using. But you can see here a nice little table output of the different subjects, and then the column is actually labeled here, just like we were working with a table in any other type of software. So they're really nice because they're really easy to read. They can still contain your data, but it pairs a lot of really nice metadata right in the data structure with it. So how do you create a data frame? There are a lot of ways to create a data frame, including reading directly from a database. I'll show a few of them right now. So here's a really big NumPy array that contains some data about some planets. So this is just the way the array looks once I've saved it. I can then pass that array into pd.dataframe, and then you can tell it what the column's name should be and what the index is. So what the row names should be. And it turns that into a really nice table of the mass, diameter, gravity, and period of the different planets in our solar system. You can also you don't have to use NumPy arrays. You can just use lists of lists or lists of tuples here. So here's a list of lists that I zipped together using that same zip function that we used back when we did the dictionary comprehension. So you can see basically what I've created is a list of pairs that are the dwarf planets and their distance from the sun. And so here I'm going to turn that into a data frame. So pd.dataframe, don't ask me why, but when you do lists of lists, instead of being able to just pass it like this, like we did with the NumPy array, you have to do data equals. Some data structures that you pass in, you can just pass in directly. Some you use data equals. I don't know why that is, but just reference the documentation if you hit a stumbling block. So again, I'm going to label my columns. And the one thing I'm going to do differently is I'm going to set the index to be equal to the name column. And so here it has the distances, but you can see that the name column here is the index of my data frame and not just another column, by the fact that it is the printout here is sort of down a row. So this says this is my column, this over here is my index, and this over here is my column of data. If you have a dictionary, you can also create data frames from that. So here's a dictionary of the moons of Jupiter with their diameter and their mass. So the way I structured the data, the dictionary rather, is I have the key, which is going to turn into my column names, and a list of all of the values, and then another key, which is the other column name, and then the list of the values. And then I tell the data frame, so this is now outside of the dictionary, I tell the data frame that I want the index to be this. I could also have done another key of name and then a list of these things and then done a set index. But this is just a slightly different way to do that. But at the end of the day, what we get is Starting with a key value pair of a column name, column contents, it turns that into yet another nice table of data. So this is to compare with reading in that record array. This is the same CSV that we read in before in the NumPy example, but now we're going to read it in with pandas. And so with pandas, you do pd.read CSV, you pass it the file, and then the only other piece of information I need to give it is I want to tell it that I want one of the columns to be my index, as opposed to it auto-generating the integer index. This is the column name that contains the names of the celestial bodies, so that's a good choice because they're all unique. Then we print that out, and it already read it all in. Not only that, but it recognized that the first row of my CSV was a header and contained the column names. So without me having to do anything in terms of telling it what, giving it instructions or passing it additional information, it has already labeled all of my columns for me based on what was inside this CSV. Not only that, but if you remember in NumPy, we had to tell it that this was a string and this was a string and this was an integer and a float and a float. It automatically, when it reads in the data, can try and do its best job of guessing what it is. So it said these all look like characters, surface is a string, same thing with this one. There's no decimal points in this column at all, so we're gonna make this an integer, and then these are gonna be floats. If you do read in a CSV that has mixed data types in a column, I think the lowest common denominator, so the data type it will fall back on is it will just make it a string. So if you had a column that had a mix of like words, but also like numbers with decimal points, what it would do is the decimal points would get read in, the number with decimal points would get read in properly, but it would be a string and you'd have to turn it back into a number. So now that we have a really nice data frame that was really easy to read in of celestial body information, what can we do with that in pandas? So the first thing you can do is you can just get some information about your data frame. There's a number of methods that are baked in that you call rate on the data frame itself. So shape tells me how big it is. So we've got 14 rows and 4 different columns. We can ask for the data types. So this is where you can see that it successfully interpreted what the data type of each of my columns was supposed to be just by looking at it and making a best guess. Strings always show up as objects in pandas data type. So this basically means a string, an integer, and then these 2 columns are supposed to be floats. And that all looks right, which is great. If you want to sanity check your data when you've read it in, which I highly recommend doing, particularly if it's a larger CSV, you can call .describe, which will give you some sort of high-level stats of each of your columns. So count isn't super meaningful because that's just the number of rows, but some values that can be really useful to double check is, for example, like the min, to make sure that it didn't accidentally, or your data didn't contain and you didn't realize, like negative values for columns where that would be unphysical, like a negative diameter showing up here would be problematic. And the same thing for the max. If there's something that's unphysically large or larger than you expect for whatever reason, you can just quickly check that, print this out, and make sure that your data, the sort of bounds of your data, match what you expect it to be. And that can be sort of a good first glance of making sure that it got read in properly. So accessing data from your data frame has there's two different ways to do it. And each method has its own strengths for different types of use cases, mostly depending on what your data kind of is. The first one is using the .iloc method. So iloc, where loc is obviously short for location, is used to access data based on its location, its index location, numerical index location in the data frame. So this is going to feel the most similar and reminiscent of the way we've been accessing data in the list or the NumPy arrays. So again, it's exactly what we've been looking at. So that you do .iloc to tell it that you're using this particular syntax, and then the same thing where you ask for the the sixth column and the third row value, which happens to be 9. This is a bit opaque, but there are instances in which it might be useful. So here I get the entire first column. And you can see when I ask the data frame to return an individual value, it returns the individual value in the data type that it is. So here we got a float. But here we asked for an entire column. And since a column of a data frame is a series, that's what it returned. So here it returned, I forget what the first column, oh, the mass, it says right here. So it's returning the mass of each of the planets in that planet's data frame that we were working with. And you can see that not only does it return the values like it would if you were doing this in a NumPy array, but it also returns all the metadata that goes along with it. So we get the indexes of each of the rows, and then we also get what the column was. So there's a lot of information stored right in here without having to reference the master data frame. So you can get multiple columns. As soon as you ask for multiple columns, it doesn't return a series anymore, it returns a data frame, which makes sense. You can ask for rows. Rows similarly get returned as series, even though they're not columns, they're rows. It presents them in the same way. So that gives me the fifth row. This is actually wrong. Which is the row of the Jupiter data. So it gives me Jupiter's mass, diameter, gravity, period. And then you can get a bunch of rows and it returns a data frame instead of a series, so on and so forth. So here I'm getting, in addition to using slices, where we select a range, you can also actually cherry pick individual rows by just passing a comma-separated list of the rows or columns that you want. So here I'm saying, give me the first row and the third row, which is Mercury and Earth, respectively, and just give me all of the columns for them. So it returns me a data frame that just contains Mercury and Earth's data. Now that feels a little clunky because you have to remember which column is which index. And I'm sure there's data frames where that sort of makes sense. Like maybe your columns are, every column is a different, actually that example, every row is like a different experiment. Your experiments are actually just numbered, 0 through 10. In which case using iloc might feel very natural. But for something like this, where the columns pertain to sort of different properties of the different rows and the rows pertain to objects, using the numerical location of the data in the data frame feels a bit unnatural. So instead, Pandas provides an additional way to access the data called .loc, which allows you to access the data using the labels, so the metadata, which can feel really natural as long as you have meaningful labels. So here, planets.loc, this is the same exact thing that we returned in the previous one. I'm just using the label name instead of the number. So this will return Saturn's mass, which apparently is 568 in whatever units. I think they may be in Earth masses. Similarly, I can ask for slices of columns using, this is a little unnatural here. I don't know why you would slice from mass to gravity because the order of the columns isn't meaningful, but just to show that it's possible, here's me asking for every row for this section of columns. You can also ask for, there's certain circumstances where you don't need the loc. If you're just asking for a column, you can just index it almost like it's a dictionary and just ask for the mass, which is nice. It saves you a few keystrokes on the instances in which this will work. So here I'm saying for every planet, I want the mass and the period by passing it a slice for the rows, and then specifically passing a list of the label, mass, and period for the column names. And so this gives me the mass and the period in a data frame for each of the things. So you get the idea. Here we can ask for all the Jupiter values. And here we can ask for everything from Earth to Saturn. And this feels a bit more natural than using the numerical values. You can actually just use the labels that correspond to the data that you want. So we'll go through this pretty quickly because it's the same as, you know, using the location, the indexing patterns we just looked at. This is very similar to the way NumPy works. So broadcasting and those types of things all exist. So here, if I create a basic data frame that just has a bunch of random numbers in it, and I've just labeled the columns with lowercase and uppercase, the columns and rows with lowercase and uppercase letters respectively, you can broadcast, oops, multiple data frame. You can tell it to replace an individual element with an individual value. You can use both syntaxes. So here I'm telling it to, I want the first value and A to be set to 200. I'm going to go through these pretty quickly because I think it's a bit repetitive. So here I'm replacing the entire first column with a range of 0 through 4 and putting that in place. And again, you can use ilock or lock interchangeably to index it for the purposes of modifying the values. So here I'm replacing the entire column 1, so B, with one value using the broadcasting that was available through NumPy. So how do you do math with data frames? Math with data frames feels just like doing math with NumPy arrays, except that you get to take advantage of all of the new powerful indexing and via labels, the column names and the index names that are in data frames compared to the record arrays. So here I'm asking it to calculate the volume of each of the Jupiter's moons. So we take the moons, I ask for diameter, the diameter column, and then I just perform a mathematical operation on that entire column. And that returns me, since this is a data frame, moons is a data frame, this returns a series with the result. And you can actually add it directly to the data frame. And this feels a little bit like the way you add things to a dictionary. So the way you add a new column to a data frame is you take your data frame and then you put the new key, just like you would in a dictionary, but this here, instead of a key, what you're passing is the new column name. And then you pass in what you want the contents of that column to be. So here I'm asking pandas to create a new column in my data frame for the volume based on that mathematical operation that we just did on the diameter. So then if we print out moons, you can see that there's now an additional column contained in the data frame for volume. And so this can be really powerful for any type of derived quantity that you would want to contain in your data based on any of the previous columns, and just store that in there as well. And you can do math using 2 or more columns to even derive yet another column. So here, if you divide the moon's mass by the moon's volume, and add it to the data frame, we now have an additional column that contains the density of each of the moons. So those are the basics of doing math on your data frame. So now we're going to get into some of the more database-y like operations that are in pandas that aren't just sort of a cleaner version of what you can do in NumPy, which I think is largely what we've looked at so far. These are some really new powerful things that would be quite clunky to try and do without pandas. So one of the most powerful uses is basically the idea that you can reorganize your data into groups and then perform all sorts of data operations and aggregations on those groups of your data. What do I mean by that? So if you remember the solar system, this is the data frame that contained the celestial body information, that contained both the mix of like the sun and the planets and the dwarf planets. So here I am asking pandas to group by the type column. So what does that mean? So it means I want it to sort of subdivide the data based on the string that is in the type column. There's a number of different strings in there. And so when you initially run this, so I'm saying bodies by type equals solar system dot group by type. It doesn't actually do any operation. All it does, so if you try to ask it to return that, it just returns this object. Basically what it does when you run this is it verifies that it is possible to do such a thing. There is in fact a group, a column called type, and it is in fact something that it could group by. When you actually want to see things, you, there's a validation. When you actually want to see the different splits, you can access them by their name. So bodies by type, and then I say get group, and then I pass it one of the types. So here I'm going to say, give me all of the gas giants. And so it does. And so it's now split up my data based on the value that was in this column. And I believe we had like star and terrestrial planet, gas giant, and maybe something else. But the important thing is you can perform a bunch of aggregations such as sums or means and other type of operations on these groups. So, so bodies by type dot mean will return the mean value of each of the columns for each of the types. So our dwarf planets have a mean diameter of this value, the gas giants have a mean mass of this value, the star, there's only one of them, so this is kind of not so meaningful. And then the terrestrial planets have, you can see here that on average, the terrestrial planets tend to be closer to the sun than the gas giants do, which makes a lot of sense with our understanding of our solar system. So just like you could with the NumPy arrays, you can use tab completion in IPython or Jupyter Notebooks to get a list of all of the aggregations available. So cumulative min, cumulative sum, et cetera, mean, median, and you can put that in here and it will return, that's not meaningful there, here, and it will return that for you. So that's the group by operations. It can be really powerful when you have data that is basically categorized by one of the columns. You can then use that category to look at this, to split up and look at subdivisions of your data very quickly. You can also filter data frames by using a series of Boolean operators. So the way you do this, and I think at first blush the syntax can seem kind of clunky, but once you understand it, it at least makes sense. So the way you do this is what I'm asking pandas to do is to give me the part of my data frame for all of the objects where the mass is greater than 1. And the reason the syntax is the way it is here's the condition that I'm trying to meet. So solar system, mass column, the value in the mass column is greater than 1. What this does is creates what's called a mask. And so it creates basically a list that says true or false for each row, is the mass greater than 1 or not? And then what I'm doing is passing that mask to the data frame itself. And then it just returns everywhere where the mask equals true. So that's why it is the way it is. You don't need to understand that necessarily. If you just remember that you put a condition inside the data frame that you are, you're trying to index. You index it by the condition, basically. And so true, it does only return me the elements in my data frame where the mass was greater than 1. You can also, it doesn't have to be a numerical operation. I can just say, give me everywhere where the type matches the string terrestrial planet. So here are my terrestrial planets. And there you can get sort of increasingly complicated, and you can actually include multiple conditions and multiple different ways of filtering your data. This can be a good way of capturing different sections of your data for something that might not be categorized. But instead you have different bounds where you want everything that's under or over a value. So if you have more than one data frame, how do you get them to work together? There are multiple different ways to combine data frames depending on what kind of, how you're trying to combine them, what you want the resulting data frame to look like. So I'm gonna sort of walk through the most useful or commonly used methods. But if you are trying to do any kind of merge, join, or concatenation, at this point, I would recommend, once you know what your problem is, like what operation you're trying to perform, go look at the official Pandas documentation, because it does a really good job of explaining not only all the different ways you can combine them, but the different, but how to do it, very good examples, very good descriptions of the differences, which sometimes can be subtle between the different operations. So the Pandas documentation is really good. But we'll show the most common ones today. So the first, sort of working our way up in complexity, the first way we're going to show is just a simple append. So I have two types of data, or two data frames rather, that have the same columns, they just contain different rows. So maybe this is an instance in which you ran the same experiment on two different data sets. So it returned the same column names, but you have different rows because they were two different versions of the same experiment. Maybe the different rows are different times or different sample names or something like that. So the first thing I'm going to do is sort of, this is a bit contrived, but just divvy up my data into things that are dwarf planets and not dwarf planets. So I have a small bodies and a large bodies data frames that have the same columns. And so the way I would mush them back together is to use append. So you take one of your data frames that already exists, and then you do that you want to sort of be your master, and then you do the main data frame dot append, and then the additional data frame with the new rows you would like to add to it. And so what that does is it adds them in as well. And what it does is it actually sticks them at the bottom. So it truly is an append. A concatenation is similar to append, except that an append is very rigid, in which the two data frames need to have exactly the same columns. A concatenate loosens that a little bit. So the column all of the columns in the first data frame don't need to appear in the second data frame. And you can also concatenate an arbitrary number of data frames in one go, unlike append where you're going to do it one at a time. So to concatenate, you do pd.concat, and then you pass it a list of the data frames you would like to tack onto each other. And basically the way it is a little bit more relaxed than an append is if a column exists in one data frame but not in the other, it will fill the column, it will fill in that column in those additional rows just with NaN values. So you'll see here, if we take the planets data frame we had before that just had the main planets of our solar system, and then we also had that moons of Jupiter. If we concatenate those together, the planets had mass, diameter, gravity, and period, and the moons also had mass and diameter. They don't have gravity and period, and instead they have volume and density. It still let me smush them together, but then it just filled in NaNs everywhere where it didn't have a matching column. And so this can be useful if you just want to smush it together and then sort it out afterwards and throw away the NaNs or set them to 0 or do whatever it is you wanted to do. Or maybe you only want these columns. You can use a concatenate to be a little bit more relaxed about your joining. So both concatenations and appends are only used to join additional rows to an existing data frame or into one master data frame. If you want to join data frames where you actually have the same rows, but you want to be adding on additional columns, then what you're talking about is a join or a merge to add these additional columns. So say we create a new data frame that has the moons of Jupiter in it, but it contains the period, which is a column that doesn't appear in the other one. We can join them by doing this. So we take the original ones, this is the one that has all 4 of those columns, dot join, and then I pass it the new data frame that I would like to tack onto it. And so that will match up all of the values in period, the period data frame on the index and put the numbers in the right place. This can get very complicated. This is a very simple example, but you can get very fancy and very powerful with this. You can have it join, if you have another column which is uniquely identified but is not your index, you can actually join on an additional column. I think, I forget exactly what it's decked in, but it's basically something like on, and then you pass it a column name. And then it will match the data based on that column name, which needs to appear in both data frames, as opposed to matching on the index. This can be useful if you have an index that isn't particularly meaningful. Maybe it's just the auto-generated one, or the index isn't important. It will just tack on this column, the columns that are present in this data frame, onto this data frame, adopting its index, but merging on to the column that you specified. So again, if you're doing any kind of more complicated joins, I recommend just looking at the pandas documentation. It does a really nice job of talking about inner joins versus outer joins and all of the ways in which that can get kind of messy. So we've mostly been talking about numerical data. We did a little bit with the type of the planet, but there's actually a bunch of powerful stuff that pandas can do if you have text-based data or time series data that we haven't really looked at yet. So most of the operations, sort of the indexing, the grouping, aggregation, filtering, is the same with non-numerical data. But there's a few actually additional features that Pandas provides for working with type data that's not numerical. So text-based data. So here, this is a data frame I'm reading, or CSV I'm reading in to a data frame using read CSV. Again, you just do read CSV and you pass it a CSV. And as long as you have a header column and some things like that in your CSV, it does a really nice job of auto labeling everything. These are jobs that were run on the cluster that have been de-identified. So this is some information, the ID of the job, the user ID, the group ID, what partition it ran in, and then some information about it, what application was run, and then whether or not it was parallel. So MPI is a type of parallelism, so whether or not it was parallel. This is actually a calculation that I did a while ago for some metrics we were generating. And so we're going to do something, other than the ID, which is really just an index. We could have said this is the index. All of this data is not really a number that's a meaningful quantitative value. So instead, we're going to do some text-based. So the first thing I'm going to do is I can ask it in the applications column to count up every time an individual value appears. So this is a way for me to figure out what the most popular packages that are being run on the cluster are. So R, it was run 4 times, Python was run 3, Spooky was run 3, et cetera, et cetera. But then you can get really fancy. So this is the calculation I actually did, where I asked it, I wanted to figure out how many parallel jobs each type of group is using. So what I did is in the denominator here, I asked it to do a value count of the groups. So this is how many jobs each group ran. And then here I'm saying of the jobs that where MPI was equal to true, again, count how many of those jobs belong to each group. So this tells me that group 1, 2/3 of their jobs had MPI equals true. Group 2, it was a little bit more than a quarter, and group 3, it was half of their jobs. And so this is a way that still using pandas, you can get some statistics on tabular or text-like data. So there's a lot of really powerful stuff for time series data too. I haven't played around with this quite as much, but their documentation is really good. So if you have time-based data, it's good to know that this is available and know all of the ways that you can do things with it. So for this example, what I'm going to do is I've set up a date range in Python and Pandas, starting on the January 1st of 2011. I'm telling it I want 72 periods, each of which is an hour long. And so this will create a range of 72 hours starting on New Year's Day. And then I want the series to just contain a bunch of random numbers and the index to be this date range. So I'm telling it that this is going to be a time series data frame. And so what it prints out is the date time object is my index. So you can see it did in fact create. This head is just showing me the top 5 rows. So the top 5 rows are the first 5 hours, and then this is just a random value in the column for whatever data. And it also prints out in this series what the frequency is. It knows that this is time-based data, and it says that the frequency is hourly. So one of the cool things you can do is you can index with ranges of times, and the times don't need to match exactly the frequency. So it's not like I can only index with hours. I can index on the half hour, and it will just give me the data that falls within that. So this is a bit contrived, but say you had like daily data or like weekly data and you indexed by month or something. It would just give you everything that falls into those categories. So here it gives me everything that falls between these two times. You can also change the frequency of the data. So if you had data that's smooth, you can ask it to do some interpolation and change the frequency. And then if there's any kind of gaps, so say you actually try to extrapolate your data, you can tell it what to do. And there's lots of different methods for this. This is using a pad forward fill, but there's a bunch of different ways you can, again, take a look at the documentation and see what's available. But here I'm telling it to just bin my data at a 45-minute interval instead of an hour. I've used this before where I had monthly data and I wanted to convert it to quarterly data. You can even do something like that. And so here it interpolates the data, and sometimes it'll rebin it. So if you go from monthly to quarterly, it does like you can do like a sum in order to put those together, or whatever actually makes sense for your operation. So here you can see that the data is now every 45 minutes, and this interpolated my random data. So this isn't particularly meaningful, but it again knows that these are now 45 minutes. So all of these operations can be performed using timestamps, which basically is like the time of the day. But you can also use periods of time. So you could, if you had quarterly data, you could say actually like the quarter, like quarter 4 of this year. And you can also use epochs, whatever sort of timestamp pattern you are using. It supports a surprising number of them. So that's everything about data frames that we're going to talk about today in terms of the properties of it. One interesting caveat about data frames, and this is a little bit related to the views thing with NumPy arrays, is that a lot of things in pandas may have felt very similar to what we looked at for NumPy, and that's because they are. Under the hood, a data frame is actually just a NumPy array with a bunch of additional sort of functions and methods built on top, which means that when you create a data frame from a NumPy array, they actually, so this sort of, it's kind of like the views inside of a NumPy array. The data frame and the NumPy array actually still point to the same place in memory. So if we create a random data frame here from, so M is our NumPy array, and then df is the resulting data frame. If I change a value back in the NumPy array, so I change the first element to 10, my data frame also gets updated. I have yet to find a place where this was super powerful, but it seems like a useful thing to know that you don't have to, so when you have your NumPy array and you create a data frame from it, if you need to do something that's more natural in the NumPy array, or you need to do something that's more natural in the data frame, you can just do it in the most natural place and both will be updated, which is kind of cool. The other thing to keep in mind with data frames is that some methods don't edit your data frame in place. Instead, they will create a new one. So if we use assign to create a new column, so here I'm assigning, this is a bit clunky, but data frame df.assign, and then I'm telling it that I want the absolute value of the C column to be added as a column called B. Which here we don't have any negative values, so it's the same. It added a new column, but wait a minute. I'm not sure what's going on with this example, but there's certain operations that basically when you run, oh, I remember why. I overran it. So if I just run df.assign, it will, and then look at df, oh, I overwrote it. Okay, sorry. There was a change in here from the previous time I ran this example. So we start over. This has only got 3 columns, A, B, C. And then here, if I try to add a new column, I'm not sure why it's not working. There are certain operations, yes, here. When I print this out, you can see the new column, but then if I actually try to use df again, the D column is missing. It didn't actually get added. The way you can get around that is by doing the df equals and then the operation, which is what I had before, which will overwrite df with the modified version based on the operation you did. But the other thing you can do is you can use the in place argument. And this is what I do most of the time, is you just do in place equals true. And most operations that don't return a new data frame as opposed to overwriting, just sort of editing the existing one, has this as an option, in which case it will just update it without having to do it. So just something to be aware of, that you might run this and it looks right, and then you actually go to do something with it and it's not there. It's probably because it didn't actually generate, because it generated a new data frame as opposed to updating the new one, and you just need to add the in place equals true. So that's everything about pandas, and then with the remaining time we'll do a little bit on matplotlib, just showing the basics of it. But before we do that, were there any questions about pandas? Great. On to matplotlib. So matplotlib is by far and away the most standard plotting package for Python. It's really powerful, but sometimes kind of not intuitive how to use it. Making really basic plots, excuse me, is really simple. Making plots look exactly the way you want them to for like publication purposes or presentation, for example, it can do it, but you just will need to look up the specifics of exactly how to change the tick marks and those types of things that you might want to do. But the documentation for matplotlib used to be really bad, but they've done a lot of work on it over the last couple of years, and it's really actually quite good now. So if you go to matplotlib.org, specifically their gallery, if you go there, you can see all of the different types of plots you can make. So the bar graphs and the pie charts, et cetera, et cetera. But they actually include example code for how they, like every line of code they wrote in order to generate their example, which can be really sort of instructive as to how to make something look a certain way. Plus their general documentation on what what parameters you need to pass in order to get certain features of your plot changed. Good. I'm actually not familiar with Seaborn. It may be sort of a better way. I know a lot of people still use Matplotlib for making basic plots. I'll look into Seaborn. Maybe I'll update this with some information about that. So for doing some 2D basic plotting in Matplotlib, you import Matplotlib this way. So import matplotlib.pyplot as PLT. This is another one of those conventions. So the first thing I'm going to do is just create an X, part of my X-axis, where I'm saying from 0 to 2, I want a NumPy array that has linear spacing of 20 elements. So this gives me a 20 element array, linearly spaced from 0 to 2. And so to plot some really simple things, the syntax is plt.plot, and then you pass it your X value, your Y value, and then you pass it all of the different values and parameters for changing the way that it looks. And then once you've finished constructing the way you want your plot to look, you can have it show up by doing plt.show. So you do a bunch of plotting operations, and then when you're ready to look at it, you do plt.show, and that's when it actually renders the plot. So this thing I've added here at the end is shorthand for I want red circles. There's lots of cute shorthands. There's also a lot of long hands that are much simpler to read. So it does a pretty good job right out of the box of setting some ticks, tick marks in the ranges that are reasonable. But again, you can change all these things if you need a logarithmic thing, or you need the labels on the ticks, or you need the ticks to appear a certain way. All of that goes as different arguments inside here or in an additional PLT row. So those are the basics, sort of X, Y, and then formatting parameters, and then plt.show to show it. You can change up a lot of things pretty simply. So here I want a blue line. That's what this shorthand means. And again, just show it. You can plot multiple. So as I said, you can construct your plot, and then at the end, you ask it to render it. The reason why these are two different steps is you can actually add multiple lines or to the same figure. So here I'm saying I just want to plot X against X, and I want green double dashes. I want X in the square root of X with red circles. So these are the two plots, and then in blue lines. So these are the two plots that we did before. And then once I just keep calling plt.plot to add things to the same plot. And then when I'm done, I do plt.show, and it will show it. It will actually render them all together in the same figure. So the way to think about Matplotlib plots is you actually have two pieces to every plot. You have the figure, which is the which can be thought of as almost like your canvas. So it's and a figure can contain multiple plots. So a plot is like a set of axes, and the figure is sort of the canvas that it sits on. And so you can have multiple sets of axes, multiple plots, all within the same one quote unquote figure. So here's how you would set up multiple plots in a figure. This is one of a number of ways. I like this way because it's fairly straightforward to know what you're working with. So this is using the subplot method. So plt.subplot, and the syntax here is a little clunky, but basically it says I want one row, 2 columns of plots, and right now I want to be editing the first one. And I always think it's really weird that this is not 0 indexed, but it's not. So this is actually truly the first plot, and I want that to be, XV, just sort of a straight line with green double dashes. And then I want to move on to the other plot in my figure. So same thing, there's going to be 1 and 2. These need to match. And then I want to be working on the second one. and then I'm going to plot the blue line, then do plt.show, and it will plot them next to each other. And again, you can get real fancy with exactly what the shape of your figure is. It normally, out of the box, always does a figure that's kind of, a little bit more rectangular than square, but, fairly square. So instead of creating two figures like we had before side by side and have it be bigger, it used the same figure size and just smushed them. But you can change the figure size to make it look however you want. Again, we're using all of the sort of additional parameters that are available to you. So these are how to show a figure, which is really useful if you're in a Jupyter notebook. But most of the time we're either on the cluster where we're running a script and we just want to save a figure to a file, or we want to save a figure to a file to go into presentation or a paper. The way you do that is you set up the plot the same way, however many plots you want, and then instead of doing plt.show, you do plt.savefig, and then you give it the name of the file you want. And Matplotlib is actually really smart in that it will infer from the file extension what you want the file format to be. So this will create, just because it says .png, it will in fact create a PNG. And if I want it to create a PDF instead, all I do is change this to .pdf, and Matplotlib says, okay, I'm going to create a PDF for you. And you can actually add different parameters to it for a PNG versus a PDF are available based on what it infers to be your file format, which means that if you put sort of a nonsense file format in here, I think it will just barf and say, I don't know what you're talking about. I don't know how to make a whatever. But it can make the most common ones that you will want to make, like a JPEG, a PNG, and a PDF. And you can do things like change the DPI and those types of things to sort of manage your file size or have it look particularly good for publication. You can also plot, so those are examples of plotting from lists or NumPy arrays, but you can also plot from a data frame, which can be nice for, it might get a bit much if you're trying to make a publication-worthy image, but it'd be good for like sanity checking your data. So if again we go back to our dwarf planets, and so we created a dwarf planet list, we convert that into a data frame. So now we've got the names of the planets and their distances from the sun. We can just plot distance. So this is my data frame. I ask it for the distance column, and then you just do plt.plot. And so it will plot the distance. The x-axis here is a little bit meaningless. It's just plotting the index. So this is our first row, second row, third row, blah, blah, blah. But it can be a good way to sort of make sure that if, for example, you have time series data, to make sure if you expect it to be smooth, it is kind of smooth, things like that, that there's no weird spikes in your data. This can be an alternative to sort of combing through the data for particular mins and maxes. You can just plot individual columns and visually look at it and check it that way. And you can get a little bit fancier with adding, changing the style and adding column. But I think if you were going to get into the level of changing your ticks and those types of things, a data frame might be a bit much. You might want to just return the values and then use the standard Matplotlib format for doing that. So that's everything I have today. Let me know if you have any questions. All of the slides are available on GitHub. I think Christine has posted the link to the GitHub up there. There's a couple small tweaks in this I'll try and push up today, but all the same content should be there. So yeah, any questions before we leave?
I'm going to post the links again, including the link to the survey. If you would all please fill out our survey, give us some feedback. That would be fantastic.
Do you have any recommendations for a development environment for Python?
Yeah, so if I'm tinkering with data for, trying to refine, like if I'm working with pandas data and trying to refine like what exactly I'm going to do with it, I like to use Jupyter notebooks for that. because it's really nice because you can sort of, particularly if you're working with larger data, you can read it in once and then you can just keep tweaking, you know, sort of whatever your query or calculation is without having to, you know, if you did it in a script format, you'd have to read in all of the data every time you wanted to like change something. And so like refining plots, refining sort of any type of operation on data frame, I like to do in a Jupyter notebook. And then if I'm going to be running it in production, I'll, you know, there's fairly easy ways to turn Jupyter notebooks into scripts. I don't use any kind of IDE for Python. I know some people have, like, I think there's one called Spider, but they're honestly not. Python, because Python's not compiled, IDEs are good for, you know, keeping track of your variables and some things like that. But because it all sort of runs in real, you know, interpreted from beginning to end, you can get pretty far with just like print statements and checking things like that. So yeah, I don't have a recommendation for a really good IDE, but Jupyter notebooks are really powerful.
You were saying that like you can generate scripts from Jupyter notebooks. Can you go the other way from like IDEs to Jupyter notebooks?
Yeah, I think you can. I don't know how it would divvy up the cells. So you can just paste, you know, just copy a script and paste it into a Jupyter notebook and then just split up the different contents into different cells so you can run them, you know, sort of not necessarily always from start to finish. I'm not sure if there's a package that is useful for just like straight up, you know, putting every line into its own cell or something, but there might be. Any other questions? Great. Well, thank you all for coming and attending our virtual workshop. We will be continuing to do them these ways until, you know, for the foreseeable future. Let us know in the survey how it's been working out. We've been doing a few so far, and everybody's working out the kinks in their workflows, but let me know if there's anything that could be done better in this sort of format, and we'll do our best to improve. Thank you.